Just for fun, I'd like to know a root of the polynomial x to the fifth plus x squared minus 1. So here's the function where I want to find a root, right? I want to find some input that makes this function equal to 0. What do I know about this function? It's continuous, and I know that f of 0, if I plug in 0, it's 0 plus 0 minus 1, so f of 0 is minus 1, and f of 1, that's 1 to the fifth plus 1 squared minus 1, that's 1 plus 1 minus 1, that's 1. So what I know here is I've got a continuous function, and its value at 0 is minus 1, and its value at 1 is 1. So there has to be some input between 0 and 1 where this function's output is equal to 0. So I know there's a root there between 0 and 1. Let's find that root. Now, if we were just trying to find where some linear term was equal to 0, you can just solve for x in that case. If I were just trying to figure out where some quadratic was equal to 0, there's the quadratic formula. If I were trying to figure out where ax cubed plus bx squared plus cx plus d was equal to 0, I could use a more complicated formula. It's the cubic formula. It's way more complicated than the quadratic formula, but there is such a formula. If I were trying to solve an equation like this that started with an x to the fourth term, I could use the quartic formula to do that. The bad news is that here I'm trying to solve a quintic, and there is no quintic formula in terms of the usual arithmetic operations, plus, minus, times, and divides, and taking roots. Of course, some quintics can be solved. I mean, it's true, right? If I'd instead been trying to find a solution to this equation, x to the fifth minus 2 equals 0, I'm looking for some value of x, take its fifth power and subtract 2, I get 0. Yes, I could solve this quintic, right? I mean, a solution is the fifth root of 2. But in contrast, this particular example, x to the fifth plus x squared minus 1, can't be solved in the sense that I can't write down using fractions, plus, minus, times, divides, and the taking of roots, a number which, if I take its fifth power, add it to its square, and subtract 1, I get back 0, right? I mean, that's the sense in which I can't solve it. I can't just write that thing down in terms of the operations that I have at hand. Knowing that requires something called Galois theory. So in light of Galois theory, what does it even mean to find a root? Well, I'm not going to be able to write down the root, but I can at least approximate the root by using Newton's method. So I can use Newton's method to at least approximate a root. So here's the function whose root I want to approximate. Right? I want to find some input so that f is close to 0. And I'll first differentiate f. So the derivative of f, well, the derivative of x to the fifth is 5x to the fourth. The derivative of x squared is 2x. And the derivative of 1 is 0. So I've got my original function, I've got my derivative. And then Newton's method tells me that I should make a first guess. My first guess will be 1. So I've made my initial guess. What's my next guess? So my next guess, according to Newton's method, I'll call that x sub 1, will be my old guess minus the function's value at my old guess divided by the function's derivative at my old guess. Now my old guess is 1. The function's value at 1, that's 1 to the fifth plus 1 squared minus 1. That's 1 plus 1 minus 1. That's 1. And the derivative at 1, well, that's 5 times 1 to the fourth plus 2 times 1. That's 5 plus 2, that's 7. So my new guess is 1 minus 1 over 7. That's 6/7. So that's my new guess. And 6/7 really isn't that bad of a guess. So my original guess, right, x0, that was 1, and f of 1 was just 1. My next guess, x sub 1, that was 6/7, right? And what's f of 6/7? Well, that's 6/7 to the fifth plus 6/7 squared minus 1. That turns out to be about 0.197, right? So certainly this 6/7 is a better guess than 1. Now, armed with my better guess, I can apply Newton's method again and hopefully arrive at an even better approximation to the root. So I can get a new guess, x sub 2, by taking my old guess, x sub 1, and subtracting the function's value there, divided by the function's derivative there. And when I do that, I get something which is about 0.812. X sub 2 is an even better guess. So I evaluate my function f at x2, I get, well, it turns out to be about 0.014. So this new guess for the root of my function is even better than my old guess, right? My old guess was giving me 0.197 as the output. This new guess is getting me closer to a 0 of the function, it looks like. Well, don't stop. I'll do it again. I can do Newton's method again, right? And I'll get a newer guess even, x sub 3, which will be x sub 2 minus f of x sub 2 divided by the derivative of f at x sub 2. And this turns out to be about 0.809. This last guess is even better. And this is really working quite well. F at this new guess, x sub 3, turns out to be about 0.000085. And I'm getting much closer now to the actual 0 of this function. These sorts of examples, polynomials where I can't explicitly write down the root, they really raise a fascinating question as to what it even means to find the root. Right? The intermediate value theorem promises me that there is a root, in this case between 0 and 1. And Newton's method, or this bisection algorithm, permits me to get better and better approximations to that root. But it's only in that sense that I can ever find the root. It's in the sense that I can get as close as you want to that root.